Just as I managed to optimize my personal hardware rig for the Qwen 3.827B release, Alibaba went ahead and dropped yet another model. But the real headline here isn't just a simple version bump. Qwen 3.8 Flash Next is a fundamental shift. It's an experimental preview of the actual architecture that will define Qwen 4, effectively giving the community a head start on this entirely new framework. So, it's kind of a sneak peek. They're showing us the blueprint for the next generation. Okay, let's unpack this blueprint. We are looking at a model with 125 billion parameters. On top of that, there is an additional 51 billion parameters dedicated to an n-gram embedding table. And finally, a 4 billion parameter multi-token prediction, or MTP. So you add that all up, you have a 176 billion parameter behemoth. Yeah, it's massive. But it's an extremely sparse MoE model because it only activates 6 billion parameters. You know, there's a fascinating subplot unfolding in the open-weight AI space right now. Which architectural philosophy will ultimately claim the crown? On one side, you've got the powerhouse dense models like Qwen 3.827B, which have really been dominating the scene lately. On the other hand, you have the mixture of experts, or MoE approach. Now, it's hard to make a direct comparison with those massive closed source trillion parameter models where we only guess at the active parameter count. But the signal here is getting very clear. This new Qwen 4 framework is a strong indicator that in the future, Qwen is going to be MoE dominant. It's not just because this Flash Next preview uses that architecture. It's because of the sheer level of engineering investment the team has poured into perfecting this specific framework. Once you see the breakdown, you'll realize they are betting the farm on this blueprint. Let's discuss first the context handling in Qwen 4. You know, if you are feeding an AI a massive PDF, a whole code base, or like a long screen recording, standard models just choke. They try to pay maximum attention to every single word simultaneously, and the math for that scales quadratically. The longer the document, the exponentially slower the model gets. Now, Qwen 3.8 Flash Next boasts a native context window of 262,144 tokens. To actually make that usable, Alibaba had to completely rethink the attention mechanism itself. And they did this by splitting the workload. So, out of the model's 48 layers, 3 out of every 4 layers use something called gated DeltaNet, or GDN. And the easiest way to understand it, GDN's job is to efficiently compress all that historical context into a fixed state. So it's not remembering every single comma and period. It's cheaply remembering the broad strokes of what happened earlier in the document. If we connect this to the bigger picture, GDN acts almost like a human short-term memory. You don't remember the exact phonetic sounds of a conversation you had an hour ago, right? But you retain the semantic meaning. GDN compresses the sequence into a constant size hidden state. But of course, sometimes you do need the exact detail, which is where the other layer comes in. Every fourth layer in the architecture uses Qwen Sparse Attention, or QSA, for precise retrieval. So the GDN layers efficiently remember the vibe, and the QSA layers precisely retrieve the exact facts when prompted. It's a brilliant division of labor. And yeah, we all know sparse attention isn't a new concept. I mean, it's been around. We have seen older models try to implement sparse attention by just scanning for important keywords and ignoring the filler words, but they have to deal with an annoying issue. they almost always end up missing the forest for the trees because they lose crucial context. So, why isn't Qwen 4, or precisely speaking, Qwen sparse attention, falling into that same trap? The reason older sparse attention failed is that it operated at the token level. It forced the model to inspect individual words to decide if they were important. When your context is a million tokens long, simply evaluating every single word to decide if you should pay attention to it becomes a massive computational bottleneck in itself. A breakthrough here in Qwen 4 architecture is its QSA does not work at the token level. It works at the microblock level. So blocks instead of individual words. So how does it decide what to look at? Instead of evaluating every token, QSA is given a strict fixed computational budget, specifically a budget of 512 blocks, which equals 2048 tokens. It scans the vast ocean of context and identifies which chunks of text, which blocks, are mathematically most relevant to the current query. It caps the attention cost regardless of how long the actual document is. So it's not trying to speed read every single word of a massive encyclopedia. It's quickly scanning the index, looking at the chapter titles and saying, I only need to open chapter 4 and chapter 12 to answer this. And the benchmark results for this are staggering. At a million tokens, this block level retrieval makes the pre-fill stage, which is when the model is reading your prompt, it makes it 7.6 times faster than standard full attention. And the decoding, the actual text generation, is 4.9 times faster. Overall, it achieves 8.6 times the pre-fill throughput of the previous generation. Okay, so the block level attention lets it read a million tokens without choking. But speed does not equal intelligence. If it's only using 6B parameters to actually think, how is it passing advanced coding tests? And here comes the star of the show, the n-gram table. Yes, the 51 billion parameter n-gram embedding table that everyone is talking about. This is where Alibaba truly separated model capacity from active computation. Here we need to be very clear about this. This 51 billion parameter layer, which is injected at layer 2 of the network, is not a neural network layer. It doesn't do matrix multiplication. It is quite literally a gigantic learned lookup table containing 20 million entries. Let's walk through this example. Say you feed the model the phrase quantitative trading algorithms. In a normal model, those words get turned into embeddings and pushed through billions of dense neural connections, calculating weights and biases all the way down, which is very computationally heavy. But Qwen doesn't do that. It takes short sequences of those words, bigrams and trigrams, and it hashes them. Let's explain that hashing process because it's the secret sauce. A hash function takes a piece of data, in this case, the specific sequence of words, quantitative trading algorithms, and runs a deterministic mathematical algorithm on it to generate a specific unique string of numbers. That string of numbers is essentially a zip code. It's an address in memory. It then takes that zip code, goes to this massive 51 billion parameter lookup table, drives straight to that exact address, and pulls out roughly 16 rows of pre-calculated data. We're talking about a tiny amount of data here, maybe a few kilobytes, and it injects that highly concentrated pre-learned representation directly into the model's data stream at layer 2. This fundamentally changes the hardware requirements. To utilize these 51 billion parameters of world knowledge, you do not have to perform massive heat-generating, GPU-intensive matrix multiplication. You are simply retrieving a tiny text file from a specific address. This creates a massive hardware loophole. You don't need expensive VRAM on an NVIDIA GPU to store this lookup table. You can offload that entire 51 gigabyte table to cheap standard system RAM. And what's wild is that you don't even need RAM because it's just a static lookup table. I went through a few discussion threads, and guess what? Users are offloading it directly to their NVMe SSDs using asynchronous prefetching. Just imagine they're reading world knowledge directly from a solid state hard drive rather than calculating it on a graphics card. But this reliance on a lookup table raises an important question. What if I feed the model a totally made up, nonsensical phrase it has never encountered in its training data? Something entirely novel like volatility, curvature, momentum coefficient. A complete word salad. It's not in the 20 million entries. The zip code doesn't exist. Does the hash function just break? Does the model crash because the lookup table comes up empty? Well, it doesn't crash, and this perfectly illustrates the beauty of the hybrid design. The lookup table will still dutifully run its hash function on those new tokens, and it will pull vectors from whatever addresses it lands on. So, yeah, basically, it pulls junk data. But surprisingly, speed doesn't get a hit because Qwen's n-gram table works via extremely sparse lookups, as we discussed earlier. For any given token, the model only retrieves 16 rows containing 160 values each. This translates to roughly 2.7 KB of data per token being read, which takes only zero point 0.1 milliseconds, while the 6B active transformer takes about 28 milliseconds to process a single token. So, the NVMe fetch is completely swallowed by the computational time of the 6B active transformer. And even though it pulled noisy data, the system doesn't collapse. The 6B parameter active transformer backbone simply takes over. It uses its deep reasoning layers to infer the meaning of volatility, curvature, momentum coefficient from the surrounding context, just like any normal large language model would do. The n-gram table isn't required for the model to function. It's just a massive boost of pre-computed world knowledge for things it does recognize, acting as a high-speed shortcut. Speaking of speed up boost, if you are in this local LLM scene for a while, this whole n-gram lookup concept might sound awfully familiar, isn't it? I think a year or two ago, local AI users were hacking together these things called n-gram speculative decoders in llama.cpp to speed up generation on slow machines. So is Qwen just taking an old open source hack and making it official? Well, it's conceptually related but fundamentally different in execution. The old llama.cpp n-grams were entirely about pattern matching to predict future tokens, right? Like an advanced autocomplete on your phone. They were just trying to guess what word you were going to type next to save the GPU some work. But Qwen's new n-gram, this 51 billion parameter table injected at layer 2, is about pattern hashing to retrieve a learned representation. It's not guessing the next word, it's providing deep, pre-calculated, dense context about the current word to make the model smarter. One is a speed trick, the other is a knowledge injection. Now, the twist is that Qwen does still have a predictive engine, but it separated that into its own module. And that is the 4B parameter MTP. The 51B n-gram embedding table helps the main model by giving it extra learned capacity. That's the knowledge retrieval. Meanwhile, at the very end of the model, the 4B MTP head helps with speculative decoding by generating multiple future token candidates at once. That's the pure speed. Qwen essentially took two distinct external acceleration hacks, perfected them, and built them directly into the native architecture. Okay, I did say knowledge retrieval, and I really need to clear up this huge point of confusion. This n-gram lookup table isn't a substitute for RAG, or Retrieval Augmented Generation. See, if you try to treat Qwen's n-gram table like a RAG replacement, the whole system is just going to collapse. In RAG, you take external documents, maybe your company's internal financial reports, and you index them into a separate vector database, right? When you prompt the model, it grabs the raw text and physically shoves it into the prompt context. It's dynamic, it's external, and you can update it in seconds just by dropping a new PDF into a folder. You never have to touch the actual model weights. But Qwen's n-gram table is the complete opposite. First, it's static. These are fixed weights that were learned during the pre-training phase. If you spend all afternoon chatting with the model and explaining your new trading strategy, that n-gram table doesn't change by a single byte. It's frozen in time. You can't just edit the table. You would need to run a full expensive fine-tuning to alter those 51 billion parameters. And the second big thing is that this table isn't actually storing documents or semantic facts. There's no vector database here, no nearest neighbor search, and it's not retrieving source text. Okay, so we covered the architecture of Qwen 4, but what does this all mean for actual performance? Does all of this actually synthesize into a good AI? Let's look at the benchmarks. Well, the benchmarks are highly impressive, especially when you look at agentic workflows, AI that actually does things on a computer. For example, on AndroidWorld, which specifically tests a model's ability to drive a real Android mobile interface and execute multi-step tasks, Qwen 3.8 Flash scores an 84.5 and Claude Opus 4.6 scores a 62.0. Just a quick heads up, I'm sticking to the officially released metrics here, so keep that in mind. It's worth noting they benchmarked against Opus 4.6, which isn't even Anthropic's top-tier frontier model. But you can see the logic there. It's hardly a fair fight comparing a massive trillion parameter beast to this few billion parameter specialized architecture. Still, if this framework is actually outperforming Opus 4.6, that's seriously impressive. And about this benchmark, if you think about it, that makes perfect sense based on the architecture we just discussed. Android World requires an AI agent to constantly look at screen recordings, parse UI elements, and remember where things were 5 steps ago. Because Qwen is using that gated DeltaNet to cheaply remember the broad strokes of past screens, it isn't burning massive compute just trying to figure out where the back button was. It holds the visual context effortlessly, and we see similar leaps elsewhere. On JobBench, it has a 19.1 point lead over Opus. And on SWE-bench Pro, which is the standard for autonomous software engineering, it beats Opus by 9.1 points. But in the spirit of objectivity, we have to look at where this architecture fails. Here is a very interesting weak spot on humanity's last exam, which is designed to be the ultimate test of expert-level reasoning. Qwen scores a 35.9, while Claude Opus gets a 40.0, which again aligns perfectly with the physics of the model. I mean, humanity's last exam tests deep, uncompressible, highly complex reasoning. It asks questions that you cannot simply look up in an n-gram table. You have to actively reason through them. And a model with only 6 billion active parameters and a relatively narrow hidden dimension is going to struggle there. It literally doesn't have the active real-time brain power for the absolute hardest logical deductions. Our subplot of dense versus MoE thickens here. Now, let's look at the API pricing. Through Qwen Cloud, they are charging just 16 cents per million input tokens and 47 cents per million output tokens. For those who are currently paying to run thousands of automated agents a day on Claude or GPT, that price drop doesn't just save some money. It makes entirely new business models possible overnight. It's less than a twelfth of what they charge for their own flagship Qwen 3.8 Max model. It shifts the economics of AI fundamentally. But what about the home users? Because despite only activating 6 billion parameters at a time, this is still fundamentally a 176 billion parameter model. When you include the n-gram table and all the dormant weights, you simply cannot run a 176 billion parameter model on a standard 12 or 16 gigabytes graphics card. Running the full unquantized model on standard consumer hardware is impossible. However, the open source community is already doing what they do best, performing absolute miracles with compression. As always, Unsloth achieved a 1-bit quantization that compresses the entire model down to just 75 gigabytes, and astonishingly, it retains 80% of its top 1 accuracy. Let's pause on 1-bit quantization for a second, because that sounds like it should destroy the model, right? How does it still work? Because of the scale. Even if each parameter is reduced to a crude binary state, the complex interplay across billions of parameters still retains the overall shape and directional logic of the data. Roughly speaking, the higher the parameter count, the better the lower quants will be. So, combining that quantization with the NVMe SSD we discussed earlier is producing wild results. Look at the Atomic chat team. They're running this 176B parameter beast on 64 gigabyte MacBooks right now. It's crazy. They are taking that massive 51 n-gram lookup table and offloading it entirely to the MacBook's solid-state drive. They're bypassing the RAM and the GPU memory almost entirely for that world knowledge. And that leads directly to my statement at the beginning of this video. Because this architecture has successfully proven that you can separate the capacity of all the world knowledge stored in the static n-gram table from the 6B active parameters during the thinking phase, Qwen 4 is highly unlikely to just be one giant monolithic model. We're looking at a fragmented, modular future. Imagine a consumer-friendly AI model with maybe 35B total parameters, but only 4B active. On its own, it would be fast, but not particularly knowledgeable. But it's built to utilize these massive n-gram tables. It could punch way above its weight class. You could run the active 4 billion parameter reasoning engine entirely on a standard cheap laptop GPU, while the vast majority of its factual world knowledge is just sitting quietly on your hard drive being pulled via asynchronous prefetching, only when needed. To summarize all of this, for the learner trying to keep up or the enterprise user trying to manage cost, the era of simply making the transformer bigger by adding more layers and more GPUs is officially over. Qwen is proving that redesigning the architecture from the ground up for extreme efficiency, separating knowledge retrieval from active reasoning, is the new frontier of AI development. It is a profound shift from scaling compute to scaling architecture. So that's it for today. Thanks for watching, and I will see you in the next video.